Welcome back to The Sleepy Computer Scientist, where we explore the digital universe one yawn at a time. I'm so glad you're here. Tonight we're going on a slow, gentle journey into something you use every single day, but probably never think about quite like this. We're going to ask a question that sounds almost silly at first, but opens up into something vast and beautiful and strange. Tonight, we're asking, does the internet have a shape? It's one of those questions that feels obvious until you really sit with it. I mean, the internet is everywhere, right? It's on your phone, in your laptop, streaming through the walls around you right now. But if you could somehow step outside of it, float above it like a cosmic observer, what would you see? What is the actual structure of this thing we're all swimming through? Before we drift into this together, I want to ask you something. Where are you right now? What city? What country? What little corner of the world are you listening from? And what time is it where you are? Drop it in the comments. I love seeing the map of where all of us sleepy explorers are scattered across the globe. It reminds me that we're all nodes in this vast network ourselves, connected by invisible threads of curiosity and insomnia. And hey, if you're enjoying these late-night wanderings through computer science, do me a favor and hit that like button. Subscribe if you haven't already. It tells the algorithm gods that there's a place for slow, soothing deep dives into the digital world. And trust me, there's so much more to explore together. Now, a quick note before we begin. This is designed to help you drift off. You don't need to remember everything. You don't need to take notes. If your mind wanders, that's perfect. If you fall asleep halfway through, even better. The internet will still have a shape when you wake up, and you can always come back to this. So settle in, get comfortable, dim the lights if you can, and let's float together into the invisible architecture that surrounds us all. Let's begin. When we talk about the internet, we often treat it like it's made of pure information, like it's this ethereal cloud hovering somewhere above us. But here's the thing. The internet has a body. It's physical. It's made of metal and glass and plastic, of copper wires and fiber optic cables, of servers humming in air-conditioned rooms and massive data centers that consume as much electricity as small cities. The internet isn't in the cloud. The cloud is in the ground. Think about it for a moment. Right now, as you're listening to this, data is traveling to reach you. Maybe it's coming from a server farm in Oregon, or a data center in Ireland, or a content delivery network node just a few miles from where you're sitting. That data is riding on light pulses through fiber optic cables, or electrical signals through copper wires, or radio waves through the air to your device. And these cables, these physical pathways, they have to go somewhere. They run under streets and through buildings. They cross oceans on the seafloor, great thick cables lying in the dark waters between continents, pulsing with light, carrying conversations and cat videos and financial transactions and love letters between people who've never met in person. There's something beautiful about that, isn't there? The internet has a geography. It has a physical presence in the world. If you were to map out all the cables, all the routers, all the servers, all the cell towers, you'd see something that looks a bit like a nervous system. Dense clusters in cities, thin threads stretching between them, thicker bundles following coastlines and major trade routes. The shape of the internet's physical infrastructure mirrors, in some ways, the shape of human civilization itself. We built it along the same paths we built roads and railways and shipping lanes. Let me tell you about these undersea cables for a moment, because they're genuinely fascinating. Right now, there are about 400 undersea cables crisscrossing the world's oceans. Together, they carry something like 99% of all international data traffic, not satellites. cables on the ocean floor. These cables are surprisingly thin, about as thick as a garden hose, though they get bulkier near shore where they need more protection. Inside there are optical fibres thinner than a human hair, and through these fibres, pulses of laser light carry data at incredible speeds. A single modern cable can transmit tens of terabits of data per second. That's thousands of HD movies every second, and they follow specific routes. The first transatlantic telegraph cable was laid in 1858, and modern internet cables still follow similar paths because, well, those are the practical routes across the ocean floor. They avoid underwater mountains, navigate around tectonic plate boundaries, and generally take paths where the seafloor is relatively stable. There are ships specially designed for laying these cables. They cost hundreds of millions of dollars and can carry thousands of kilometers of cable coiled in massive tanks. The process of laying a cable across the ocean takes weeks, slowly paying out the cable, using robot submarines to bury it in the seafloor near shore to protect it from ship anchors. And these cables break. All the time, actually. Ship anchors drag across them, underwater landslides bury them, earthquakes sever them, and occasionally sharks bite them. I'm not making that up. Sharks seem to be attracted to the electromagnetic fields or the sounds the cables make, and they'll just chomp down on them. So modern cables often include special wrapping to protect against shark bites. When a cable breaks, it can take days or weeks to fix. The repair ship has to sail to the break location, use remotely operated vehicles to find the cable on the ocean floor, cut out the damaged section, splice in a new piece, and carefully lower it back down. It's painstaking, difficult work, and it's happening somewhere in the world almost constantly. But here's where it gets interesting. The physical shape is just one layer. It's like asking what shape a city has, and only looking at the roads. Sure, the roads matter, but what about the flow of traffic? What about who talks to whom? What about the invisible connections between people that make a city alive? The internet is the same way. The cables and servers give it a skeleton, but the real shape emerges from how information flows through it. Let's think about this differently for a moment. Imagine you're standing in a dark room. You can't see anything, but you have a flashlight. You shine it around, and you start to see shapes emerge from the darkness. A chair here, a table there. Slowly, you build a mental map of the room's shape. This is basically how we understand the shape of the internet. We can't see it all at once because we're inside it, we're part of it. But we can send out little probes, little packets of data, and see where they go and how long they take to get there. We can trace routes, measure latencies, map connections. And when we do this, when computer scientists and network researchers map the internet's topology, what they find is fascinating. The internet isn't evenly distributed. It's not a perfect grid or a neat hierarchy. It's something much more organic, much stranger. It turns out the internet is what mathematicians call a scale-free network. Now don't worry, we're not going to dive deep into graph theory here. But the basic idea is beautiful and surprisingly simple. In a scale-free network, most nodes have just a few connections, but a small number of nodes are massively connected. Think of it like a city. Most streets connect to just a few other streets, but some intersections, some major hubs, connect to dozens or hundreds of other roads. These are your Times Squares, your Piccadilly circuses, your Shibuya crossings. The internet has hubs like this too, major internet exchange points where massive amounts of data flow through. Think of places like the Equinix data centers, or the Amsterdam Internet Exchange, or the DE Kicks in Frankfurt. These are the grand central stations of the digital world. Let me paint a picture of what one of these internet exchange points looks like. Imagine a nondescript building, maybe in an industrial area, maybe downtown. From the outside it looks boring, utilitarian, but inside it's one of the most important buildings in the world. Floor after floor of servers, racks upon racks of networking equipment, all humming with the sound of cooling fans. The temperature is kept precisely controlled. The power systems have multiple redundancies because these facilities can never ever go down. A single minute of downtime could affect millions of people. And in these buildings, dozens or hundreds of different networks meet. Internet service providers, content delivery networks, cloud hosting companies, they all bring their connections here, and they literally plug into each other. Physical cables connecting one network to another, negotiating the exchange of traffic through something called peering agreements. This is where the internet actually happens, in a sense. This is where separate networks become the internet, capital I. These are the crossroads, the hubs, the beating hearts of the global network, and this creates a fascinating shape. If you were to visualize the internet as a graph, with every device and router as a point and every connection as a line, you'd see this beautiful, chaotic structure. Dense clusters of connectivity surrounded by sparser regions. A few massive hubs with countless thin threads radiating outward. It looks a bit like a neural network, actually, or like the structure of the universe itself, with galaxies clustered along vast cosmic filaments. There's a reason for this similarity, by the way. It's not cosmic coincidence, it's mathematics. Networks that grow organically, where new nodes preferentially attach to already well-connected nodes, naturally evolve into this scale-free structure. It happens with the internet, with social networks, with the neurons in your brain, with trade routes, with the distribution of galaxies. It's called preferential attachment. The rich get richer, in a sense. If you're a new website or a new network trying to join the internet, you're more likely to connect to a well-established hub than to some random, obscure node. So the hubs get bigger, the structure reinforces itself. It's one of those deep patterns that shows up everywhere once you know to look for it. And maybe that's oddly comforting. The internet isn't just some random tangle of wires. It has structure, it has shape. And that shape echoes shapes we see throughout nature and human society. But let's zoom in a little now. Let's think about what shape means when we're talking about how data actually moves through this network. Here's a thought experiment. Imagine you want to send a message to someone on the other side of the world. Let's say you're in Toronto and you're sending a message to someone in Tokyo. What path does that message take? You might imagine it goes in a straight line, right? The shortest distance between 2 points? But that's not how it works at all. The internet doesn't care about geographic distance in the way we do. It cares about network distance. Your message, broken up into little packets of data, might take a wild route. It might go from your device to your router, to your internet service provider's local server, to a regional hub, then maybe to a major internet exchange point, then across an undersea cable, then to another exchange point, then to another ISP, then to another regional hub, and finally to your friend's device in Tokyo. But here's the really interesting part. Each packet might take a different route. The internet is designed to be resilient, to route around damage and congestion. So your message might arrive in pieces, having travelled different paths, and get reassembled at the destination. It's a bit like sending a letter, where each word is written on a separate piece of paper, and each piece is handed to a different postal carrier who takes their own route, and somehow they all arrive and get sorted back into the right order. Sounds chaotic, right? But it works. Billions of times per second, all over the world, this controlled chaos is humming along. The protocol that makes this work is called packet switching, and it was one of the most revolutionary ideas in the history of computing. Before packet switching, networks used circuit switching, like old telephone networks. When you made a call, a dedicated circuit was established between you and the other person, and that circuit was yours for the duration of the call. It was inefficient because that circuit sat idle whenever you weren't actively talking. Packet switching is different. Your data is broken into packets. Each packet is given a destination address, and each packet finds its own way through the network. The network can dynamically route around problems, can balance load across different paths, can use the same infrastructure to carry many different communications simultaneously. It's the difference between a highway system and a train on dedicated tracks. The highway is more flexible, more resilient, more efficient for handling varied traffic. And this reveals another layer of the Internet's shape. It's not just the physical topology of cables and routers, it's the logical topology of how data flows, and that shape is constantly shifting, constantly adapting, like a river changing course around obstacles. Network engineers sometimes call this the dynamic topology of the Internet. At any given moment, the best path between 2 points might change based on traffic, based on which servers are online, based on which routes are congested. The Internet is less like a fixed map and more like weather patterns, constantly in motion. Think about that for a moment. Every time you load a web page, you're participating in this vast, fluid choreography. Your request goes out into the network, bounces through this shifting landscape of routers and switches, finds its way to the right server, and then the response comes flowing back to you, possibly along an entirely different path. And all of this happens in milliseconds, faster than you can blink, faster than you can think the thought. I wonder how fast this is. The protocol that determines how packets find their way is called routing, and it's absolutely fascinating. Every router on the Internet maintains a routing table, a kind of map that says, if a packet is going to this network, send it to this next router. These routing tables are constantly being updated through routing protocols, where routers talk to each other, sharing information about which paths are available, which paths are fast, which paths are congested. The most important of these protocols is called BGP, the Border Gateway Protocol. It's what allows different networks to interconnect, to form the Internet. And it's both brilliant and terrifying because BGP is built on trust. When a network announces I can reach these addresses, other networks just believe it. There's very little verification. This has led to some spectacular failures and attacks. A misconfiguration in BGP can route traffic for major websites through the wrong country. A malicious actor can hijack IP addresses, pretending to be someone they're not. In 2008, Pakistan tried to block YouTube nationally and accidentally announced to the whole world that they were YouTube, breaking the site globally for hours. The Internet's routing is a shape built on trust and collaboration, and mostly, it works. But that trust is also a vulnerability. Now let's get even stranger. Let's talk about the Internet's shape in terms of distance. Not miles or kilometers, but a different kind of distance. On the Internet, two computers might be physically next door to each other, but very far apart in network terms. Maybe they're on different networks that don't have a direct connection, so data between them has to route through several intermediaries. Conversely, two computers on opposite sides of the planet might be very close in network terms if they're both connected to well-linked hubs. Network scientists measure this with something called hop count. How many hops, how many jumps from one router to the next does it take to get from point A to point B? And what they've found is remarkable. The Internet has what's called a small world property. This is the same phenomenon you've probably heard of in social networks, the idea that you're just 6 degrees of separation from anyone else on the planet. On the internet, that number's even smaller. From any computer on the internet to any other computer, you're typically only about 15 to 20 hops away. 15 routers. That's it. You, right now, wherever you are about 15 hops away from a server in Beijing, from a computer in Buenos Aires, from someone's laptop in Mumbai. The internet is incredibly short. Its diameter, in network terms, is tiny. This gives the internet a kind of crumpled shape, if you want to think about it spatially. Imagine taking a huge piece of paper, covered with dots representing every device on the internet, and then crumpling it up into a ball. Suddenly, points that were far apart on the flat sheet are close together in the crumpled ball. That's kind of what the internet's topology does to distance. Geography becomes almost irrelevant. Network connectivity is what matters. This is why you can have a video call with someone on another continent with almost no lag, but sometimes have trouble loading a page from a local server. It's not about the miles, it's about the path. And there's something deeply weird and wonderful about this. The internet collapses distance. It makes the world smaller, not in a metaphorical feel-good way, but in a real, measurable, mathematical way. The shape of the internet is a shape where everywhere is close to everywhere else. But here's something interesting to think about. This compression of distance isn't uniform. Some places are more compressed than others. Countries with good internet infrastructure, with connections to major hubs, are closer in network terms to the rest of the world than countries with poor infrastructure. You can be physically in the middle of a major city, but if your country's internet connectivity is limited, if you have to route through distant servers, you might be farther away in network terms than someone in a rural area of a well-connected country. This creates a kind of digital geography that doesn't match physical geography. There are network continents that don't correspond to real continents. There are network neighborhoods of devices that are close in connectivity terms, even though they're scattered across the planet. And this has real consequences. It affects the speed of your internet. It affects which content you can access easily and which requires long, slow routes. It affects where companies decide to place their servers. It affects economic opportunities, access to information, participation in global conversations. The shape of the internet is, in some sense, the shape of privilege and access in the digital age. You might be getting sleepy now, and that's perfect. Let these ideas wash over you. The internet as a nervous system. The internet as a crumpled ball of space. The internet as a living, shifting river of data flowing through invisible channels. These aren't just metaphors. They're different ways of understanding the same strange, beautiful structure. Let's drift into another layer now, something a little more abstract but deeply fascinating. We've talked about the physical shape, the topological shape, the shape of data flow. But there's another way to think about the internet's shape, the shape of information itself. Imagine the internet not as cables and routers, but as a vast library. Every web page, every video, every social media post, every email, it's all information stored somewhere. And all of this information is connected through links, through hyperlinks, through references, through the ways we navigate from one piece of content to another. This creates what's called the web graph. And yes, this is where the World Wide Web gets its name. It's a web of connections. If you were to map this out, every web page is a node, and every hyperlink is an edge connecting nodes. And this graph, this web, has a shape too, and it's fascinatingly strange. Back in the early 2000s, researchers did a massive study where they crawled billions of web pages and mapped out the structure of the web. What they found was surprising. The web isn't one big connected whole, it's more like an archipelago, a collection of islands with a massive central continent. They identified several regions. There's what they called the strongly connected core, a huge cluster of pages that all link to each other, directly or indirectly. If you're on a page in this core, you can get to any other page in the core just by following links. Then there's an in region, pages that link into the core but that you can't get back to from the core. Think of these as feeder streams flowing into a river. There's an out region, pages you can reach from the core but that don't link back to it. These are like tributaries flowing out of the river. And then there are tendrils, pages that are connected to the in or out regions but not to the core itself. And finally, there are completely disconnected components, little islands of web pages that don't link to or from the main structure at all. When you visualize this, it looks a bit like a bow tie. The core in the middle, the in region on one side, the out region on the other, and tendrils and disconnected bits scattered around. This is the shape of the web, or at least it was. The web is constantly growing, constantly changing, so this shape is always evolving. But the basic structure seems to persist. And there's something almost poetic about this, isn't there? The web isn't a perfect, orderly structure. It's messy. It's organic. It has a core and a periphery. It has dead ends and isolated pockets. It's like a city that grew without a master plan, sprawling and chaotic and yet somehow functional. Think about what this means for a moment. If you're trying to get from a page in the in region to a page in the out region, you have to go through the core. There's no other way. The core is the bridge that connects everything. This is why search engines are so important. They're guides through this maze. Without them, without something to help you navigate, large parts of the web would be essentially undiscoverable. You'd be trapped in one region, unable to find your way to another. And it raises interesting questions about visibility and power. Who controls the core? What pages are in the core and what pages are left out on the periphery? Who decides which pages get linked to and which ones languish in obscurity? The shape of the web is, in many ways, the shape of attention and influence in the digital world. Now, there's another fascinating aspect to the web shape that has to do with how deep it is. When you use a search engine, you're only seeing a tiny fraction of the web. The surface web, the part that's indexed by search engines, is maybe only 10% of the total web. The rest is what's called the deep web. This isn't anything sinister, by the way. It's just content that search engines can't or don't index. Databases that require login, pages behind paywalls, content that's dynamically generated, private networks, academic journals, medical records, legal documents. All of this exists on the internet but isn't part of the searchable web. And then there's the dark web, which is a small subset of the deep web. This is content that's intentionally hidden, that requires special software to access. Places like Tor hidden services. Some of this is used for legitimate privacy purposes, some for whistleblowing and activism in oppressive regimes, and some for illegal activities. The point is, the internet has depth. It has layers. The shape of the internet includes these hidden dimensions, these spaces that most people never see, but that are very much part of the overall structure. It's like an iceberg. The part above water, the surface web, is visible and obvious. But there's so much more below the surface, unseen but massive and important. Now here's where things get really interesting, and maybe a little philosophical. We've been talking about the internet's shape in different ways: physical, topological, informational. But all of these perspectives share something in common. They're all trying to answer the question, how is the internet organized? And the answer, in every case, is something like, it's organized, but not by design. It's structured, but not planned. It has shape, but that shape emerged. The internet is a perfect example of what complexity scientists call an emergent system. Nobody sat down and designed the whole thing. There's no central authority dictating how the internet should be shaped. It grew organically from millions of individual decisions made by engineers and companies and governments and people like you and me, all acting in our own interests, all connecting to the network in our own ways. And yet, out of this chaos, patterns emerge. Scale-free topology, small world properties, bow-tie structure. These aren't accidents. They're the inevitable mathematical consequences of how networks grow. It's the same kind of emergence you see in ant colonies. No ant understands the structure of the whole colony. Each ant is just following simple local rules, responding to chemical signals, doing its tiny part. But zoom out and you see complex organized behavior, you see structure, you see shape. The internet is like that. Billions of devices, each one just trying to send and receive data according to simple protocols. Nobody has the full picture, but zoom out and there it is. A shape, a structure, a thing with properties and patterns. And maybe that's the most beautiful answer to our original question. Does the internet have a shape? Yes, but it's not a shape anyone designed. It's a shape that designed itself. It's a bit like asking whether a forest has a shape. Well, yes, in a sense. Each forest is unique, shaped by the terrain and the climate and the particular species that live there and the history of fires and storms and human intervention. But nobody drew up blueprints for a forest. It's an emergent shape, born from countless small interactions between organisms and environment. The internet is the same. It's a digital forest, a sprawling, evolving, living system. And you're part of it. Right now, you're a node in this vast network. Your device is connected to routers, to servers, to other devices. When you send a message, when you load a web page, when you stream a video, you're participating in the constant reshaping of this structure. You're not just using the internet, you are the internet. We all are. But emergence also means fragility in unexpected places, because the internet's self-organized, because nobody planned it all out. There are hidden vulnerabilities, choke points where too much traffic flows through a single hub, critical infrastructure that's not as redundant as we might hope, dependencies we don't fully understand until something breaks. In 2021, a single company, Fastly, had a configuration error that took down huge swaths of the internet for an hour. Major news sites, government pages, streaming services, all suddenly unreachable. One company, one error, cascading effects. These kinds of incidents reveal the shape of the internet in stark terms. They show us where the critical nodes are, where the structure is most vulnerable, where the shape is perhaps not as robust as we'd like. And this raises important questions about the future. As the internet continues to grow and evolve, as more and more of human civilization depends on it, how do we make sure its shape remains resilient? How do we avoid creating single points of failure? How do we design for robustness in a system that nobody fully controls? These are not easy questions, but they're increasingly urgent ones. And here's something to ponder as you drift off. The internet's shape is still evolving. Right now, as you listen to this, new connections are being made, new servers are coming online, new cables are being laid, the topology is shifting. Some researchers worry about fragmentation. Will the internet stay as one global network, or will it splinter into separate regions? We're already seeing signs of this with things like the Great Firewall of China, with data localization laws, with regional differences in how the internet is regulated and controlled. If that happens, If the internet breaks up into separate pieces, its shape will change dramatically. That small world property might disappear. The distance between different parts of the network might grow. It would be like going from one big crumpled ball to several separate crumpled balls with fewer connections between them. But other researchers are excited about new topologies, new ways of organizing networks that could make the internet more robust, more democratic, more resilient. Let's talk about mesh networks for a moment. In a traditional network, your device connects to a router. The router connects to an ISP. The ISP connects to the broader internet. It's hierarchical. There are defined pathways and defined authorities. In a mesh network, every device is a router. Your phone can relay data for someone else's phone. Every node in the network can serve as a bridge to other nodes. Instead of a hub-and-spoke model, you get something more like a web, where connections form organically between nearby devices. Mesh networks have some beautiful properties. They're incredibly resilient. If one node fails, traffic just routes around it through other nodes. There's no single point of failure. They're also self-organizing. As devices join or leave the network, the topology automatically adapts, and they're democratic in a sense. There's no central authority, no ISP controlling access. The network is owned collectively by everyone who participates in it. There are already mesh network projects in various parts of the world. In rural areas with poor internet infrastructure, communities are building their own mesh networks using cheap wireless routers. In urban areas, activists are creating mesh networks as alternatives to commercial ISPs, as ways to communicate that can't be easily shut down or monitored. These networks are small so far. They're experiments. But they show what's possible. They hint at a different shape the internet could take. Imagine if your entire city was one big mesh network. Every phone, every laptop, every smart device, all forming a dense web of connections. Data flowing through this web like water through capillaries. No central hubs, no choke points, just a vast distributed organic network. That would be a radically different shape from the internet we have now. It would change the dynamics of power and control. It would change who can access what and how. Easily, it would change what's possible. Some researchers think this is the future, that the internet will evolve from a hierarchical hub-dominated structure to a more distributed mesh-like structure. That as devices become more powerful and wireless technologies improve, we'll move away from ISPs and toward peer-to-peer connectivity. Others think mesh networks will remain niche, limited to specific use cases, because the current model is simply too entrenched, too economically powerful, too convenient for most people most of the time. Time will tell. But it's exciting to think about. The shape of the internet is not fixed. It can change. We can change it. Now let's talk about something truly wild. Something that's not just the future but is actually starting to happen right now. Satellite internet constellations. You might have heard of Starlink, SpaceX's project to launch thousands of satellites into low Earth orbit to provide internet access anywhere on the planet. Or similar projects from other companies like OneWeb or Amazon's Project Kuiper. These constellations are launching hundreds or thousands of satellites, creating a kind of orbital internet infrastructure. And this fundamentally changes the shape of the internet in ways that are hard to overstate. Think about it. Right now, the internet's physical shape is tied to the ground. Cables running through the earth, across the ocean floor, following the paths of human geography. If you're in a remote area, getting internet access means somehow connecting to that ground-based infrastructure, which can be difficult and expensive. But with satellite constellations, the internet extends into space, into orbit. Suddenly, the shape of the internet includes this orbital shell around the planet, this network of satellites passing overhead, constantly moving, constantly communicating with each other and with ground stations. And here's what's truly remarkable. These aren't traditional satellites in high geostationary orbits, sitting 35,000 kilometers above the equator. Those satellites have terrible latency because the signal has to travel so far. It takes a quarter of a second for data to make the round trip, which makes them awful for anything interactive. These new constellations are in low Earth orbit, only a few hundred kilometers up. That means the latency is comparable to ground-based internet. Better, in some cases, because light travels faster through the vacuum of space than through fiber optic cables. A signal can bounce between satellites, taking a shortcut over the curve of the Earth, arriving faster than if it had travelled through cables following the surface. This is genuinely strange and beautiful. The shape of the internet now includes space, includes trajectories and orbital mechanics, includes thousands of satellites zipping around the planet at 17,000 miles per hour, each one a node in this vast network. And this changes everything about global connectivity. A village in the Amazon rainforest can have the same internet access as a penthouse in Manhattan. An Antarctic research station can video chat with colleagues in real time. A ship in the middle of the Pacific Ocean can stream 4K video. The geography of the internet is being rewritten. Physical location matters less and less. The digital divide, at least in terms of pure access, could shrink dramatically. But of course, it's not that simple. Satellite internet is expensive. The satellites themselves cost money to build and launch, and that cost gets passed on to users. So while the technology could theoretically provide universal access, the economics might prevent that. And there are concerns. Astronomers worry about these satellites interfering with observations, cluttering the night sky with artificial objects. Space debris experts worry about collisions, about the long-term sustainability of putting thousands of satellites in orbit. Regulators worry about spectrum allocation, about who gets to use which radio frequencies. The shape of the internet is expanding into space, but that expansion comes with complications, with questions that we're only beginning to grapple with. And then there's quantum internet. This is still mostly theoretical, still in the research phase, but it's so fascinating that we have to talk about it. You've probably heard of quantum computing, the idea of using quantum mechanical effects to perform computations in fundamentally new ways. Quantum internet is a similar idea applied to networking. In a quantum internet, instead of sending classical bits of information, ones and zeros, you'd send quantum bits, or qubits. And qubits are strange. They can exist in superposition, being both 1 and 0 simultaneously until they're measured. They can be entangled with other qubits, creating correlations that persist even across vast distances. This enables things that are impossible with classical internet. Perfectly secure communication, for instance. Quantum key distribution uses entangled particles to generate encryption keys. If anyone tries to intercept the communication, the quantum states collapse, and both parties know immediately that they've been compromised. It's security guaranteed by the laws of physics, not just by mathematical complexity. But more than that, a quantum internet would enable distributed quantum computing. You could have quantum computers in different locations working together on the same problem, sharing quantum information directly. This could solve certain problems that even quantum computers working alone couldn't handle. And here's where it gets really wild. The shape of a quantum internet would be unlike anything we've seen before. Quantum entanglement creates connections that don't have a classical analog. Two entangled qubits are connected in a way that transcends space. They're not connected by any physical medium. They're just connected, correlated, inseparable in a sense. So the topology of a quantum internet wouldn't just be about physical connections or logical roots. It would include these quantum correlations, these non-local connections that exist in a different way entirely. It's hard to even visualize what that shape would look like. It's a network where certain nodes are connected not through any pathway, but through fundamental quantum properties, where distance in some sense becomes meaningless for certain kinds of operations. Now, quantum internet is still far from reality. We've built small quantum networks in laboratories, connecting devices across a room or across a city. But scaling this up to a global quantum internet faces enormous technical challenges. Quantum states are fragile. They decohere, collapse, get destroyed by any interaction with the environment. Maintaining quantum information over long distances and long times is incredibly difficult, but researchers are working on it. There are proposals for quantum repeaters, devices that could extend quantum communication over longer distances. There are experiments with satellite-based quantum communication, using satellites to distribute entangled photons across continents. And if we succeed, if we build a quantum internet, it would represent a fundamental shift in what a network even is. The shape of the internet would extend into quantum space, into the realm of superposition and entanglement, and fundamental quantum weirdness. It's thrilling to think about. Terrifying too, maybe, but mostly thrilling. Let's talk about something a bit closer to the present, but equally transformative: the Internet of Things. Right now, when we think about the Internet, we mostly think about computers and phones and tablets, devices that we use to access information and communicate with other people. But increasingly, the Internet is being populated by devices that aren't really for humans at all. Smart thermostats, connected refrigerators, security cameras, fitness trackers, smart speakers, industrial sensors in factories, monitors in hospitals, trackers on shipping containers, sensors in cars. Billions of devices, all connected, all generating data, all communicating with servers and with each other. This is changing the shape of the Internet in profound ways. The number of connected devices is skyrocketing. There are already more IoT devices than people on Earth, and that gap is growing rapidly. And these devices create a different kind of network topology. They're not randomly distributed like computers. They're clustered in specific places. Hundreds of sensors in a single factory, dozens of smart devices in a single home, thousands of monitors in a single hospital. This creates dense local networks with different characteristics from the general Internet. Much more local communication, devices talking to nearby devices, gateways that aggregate data and send it upstream, edge computing nodes that process data locally before sending anything to the cloud. The shape of the Internet is becoming more hierarchical again in some ways, with these local clusters of IoT devices forming their own sub-networks, their own local topologies within the broader Internet topology. And the traffic patterns are changing too. Traditional Internet traffic is bursty. You load a web page, there's a flurry of activity, then quiet. You stream a video, steady flow for a while, then it stops. Human-driven patterns. IoT devices create constant steady streams of small data packets. A sensor reporting temperature every minute, a fitness tracker uploading step counts, a security camera streaming video continuously. This constant background hum of machine-to-machine communication. Network engineers are having to rethink how networks are designed to handle this. The protocols that work well for human-driven traffic don't necessarily work well for IoT traffic. The infrastructure that's optimized for delivering web pages and videos isn't necessarily optimal for handling billions of tiny sensor readings. The internet's shape is adapting, evolving to accommodate this new kind of traffic, this new kind of user that isn't really a user at all but a thing, an object, a sensor. And this raises fascinating questions. If most of the internet's traffic is machine-generated, if most of the nodes in the network are things rather than people, what does that mean for how we think about the internet? Is it still fundamentally a communication network connecting humans? Or has it become something else, something more like a nervous system for a vast distributed cyber-physical system that encompasses both people and machines? The shape of the internet is becoming less human-centric. It's evolving into something that includes us, but isn't primarily about us. And that's both exciting and a little unsettling. There are concerns about security, of course. Every IoT device is a potential entry point for attackers. A vulnerability in a smart light bulb could potentially be exploited to access the network it's connected to. In 2016, a botnet called Mirai infected hundreds of thousands of IoT devices and used them to launch massive distributed denial-of-service attacks. And there are concerns about privacy. All these devices gathering data about us, about our homes, our habits, our health. Where does that data go? Who has access to it? How is it secured? The shape of the internet is becoming more intimate, more embedded in the physical world, more entwined with our daily lives. And that intimacy brings risks. Now let's talk about something that might seem like science fiction, but is closer to reality than you might think. The idea of a biological internet. Scientists are experimenting with ways to use biological systems for computation and communication. Living cells that can process information, that can communicate with each other through chemical signals, that can be programmed to perform specific tasks. One area of research is called synthetic biology, engineering bacteria to perform computations, to store data in DNA, to respond to environmental signals in programmed ways. These bacteria could form networks, communicating through chemical signals, creating a kind of biological internet. Why would we want this? Well, biological systems have some remarkable properties. They're incredibly energy efficient. They can self-repair and self-replicate. They can operate in environments where electronic devices would fail. They can interface directly with living organisms. Imagine biosensors in your body, monitoring your health, communicating with each other and with external systems. Imagine environmental sensors made of engineered algae, detecting pollutants and transmitting warnings. Imagine smart agriculture systems where the crops themselves are sensors, reporting their own needs for water and nutrients. This would be a radically different kind of network. Its shape would be organic, literally. It would grow and adapt and evolve in ways that electronic networks can't. It would blur the line between the living and the technological, and the topology would be fascinatingly different. Chemical signals diffuse through space differently than electromagnetic signals. They create gradients, concentrations, patterns in three-dimensional space, rather than traveling along defined pathways. A biological internet might have a shape more like a slime mold than like the current internet. Tendrils reaching out, finding resources, creating efficient pathways, constantly reorganizing based on local conditions. This is still very much in the research phase, but there are real experiments happening. Bacteria that can solve simple computational problems, cells that can store and retrieve data encoded in DNA, living materials that respond to digital signals, The internet of the future might not be purely electronic, it might be hybrid, part silicon and part carbon, part machine and part organism, and its shape would reflect that hybridity, that fusion of different kinds of information processing. It's genuinely strange to think about. But then again, so much about the internet is strange when you really examine it. We've built this globe-spanning network of machines that think and communicate. We've created artificial rivers of information flowing through channels we can't see. We've extended our minds and our senses beyond our bodies into a shared digital space. Adding biology to that mix is just the next step in the ongoing process of humans creating tools that transform what it means to be human. Let's slow down a bit. Let's come back to something more grounded, more immediate. Let's talk about what the internet shape means for you personally right now. You're lying there or sitting there listening to this. You're connected to the internet through your device. That device is connected to a router. The router is connected to an ISP. The ISP is connected to regional networks. Those networks are connected to backbone networks and internet exchange points and undersea cables. Right now, in this moment, you're a part of this vast structure. You're a node, a point in this sprawling graph. And that means something. It means you're connected to billions of other people. Not metaphorically, but literally, physically connected through cables and radio waves and satellites. The signals from your device are mingling with signals from someone in Tokyo, someone in Sao Paulo, someone in Cairo, someone in Oslo. It means the information you access is shaped by the network's topology. The websites that load quickly for you are probably hosted on servers that are close to you in network terms, or that are on content delivery networks with nodes near the major hubs you connect through. It means your privacy and security are affected by the path your data takes. If your traffic flows through a surveillance-heavy jurisdiction, it might be monitored. If it passes through an insecure node, it might be intercepted. It means the ideas and information that reach you are influenced by where you are in the network structure. Algorithms decide what you see based on engagement patterns, and those patterns are shaped by the network topology, by who's connected to whom, by how information flows through the structure. You're not separate from the internet, you're embedded in it. Your position in its structure affects your experience of the digital world. And here's something beautiful to consider. Your actions change the internet's shape, ever so slightly. When you create a link from your website to someone else's, you're adding an edge to the web graph. When you share a post on social media, you're creating a pathway for information to flow. When you connect to a new network, you're changing the topology, adding new possibilities for how data can move. The internet is not something that exists independently of its users. It's made of us, our connections, our communications, our contributions. We are the internet, and the internet is us. That can feel overwhelming, maybe. The weight of being part of something so vast and complex. But it can also feel empowering. You matter. Your position in this network, your actions within it, they have ripple effects. They shape the structure, even if just infinitesimally. Every time you go online, you're participating in one of the most remarkable phenomena in human history. The creation of a collective, global, interconnected intelligence. Not artificial intelligence, but augmented intelligence. Human minds linked together, sharing knowledge and creativity and stupidity and beauty and everything else that makes us human. The internet's shape is the shape of human connection at a scale never before possible in our species' history. And you're part of that, right now, in this moment. Let me tell you something that might seem paradoxical. The internet makes the world smaller, but it also makes it more complex. Before the internet, your social circle was limited by geography. The people in your town, your city, maybe people in other cities you could reach by phone or mail. Your sources of information were limited too. Local newspapers, national television, books you could physically access. The internet removes those limitations. Suddenly, your potential social circle is billions of people. Your potential sources of information are essentially infinite. The world that's accessible to you expands dramatically. But this doesn't make things simpler. It makes them vastly more complicated. Because now you have to navigate this enormous space. You have to figure out who to trust, what to believe, which of the billions of voices you should listen to. The internet's shape creates both connection and confusion. It brings distant things close, but it also makes it harder to figure out what's actually close to you, what's actually relevant, what actually matters. We're still learning how to navigate this. We're still developing the cognitive tools, the social norms, the technological interfaces that we need to function well in a world where everything is connected to everything else. Think about how disorienting it can be. You can be reading a news article about local politics and then click a link and suddenly you're reading about a scandal in a country you've never been to. You can be messaging a friend and then get a notification about a global crisis. You can be watching a video about baking bread and the algorithm suggests something about conspiracy theories. The internet collapses context. Everything exists in the same space, the same feed, the same interface, local and global, trivial and critical, true and false, all mixed together. This is a consequence of the internet's shape, that small world property where everything is close to everything else means that you're always just a click or two away from something completely different. The lack of natural barriers, of distance, of friction, means that your attention can jump wildly from topic to topic, from context to context. Some people find this liberating, the ability to explore freely, to make unexpected connections, to stumble upon ideas and people you'd never encounter otherwise. The internet is a space of serendipity and discovery. Other people find it exhausting. The constant barrage of information, the difficulty of maintaining focus, the feeling that you're supposed to care about everything happening everywhere all at once. The internet is a space of overwhelm and anxiety. Both of these are valid responses to the same structure. The internet's shape enables both experiences. It's not inherently good or bad. It's a tool, a space, a structure. What matters is how we learn to inhabit it. And maybe that's the real challenge of living in a world shaped by the internet. Not just understanding its technical structure, its topology and protocols and physical infrastructure, but understanding how to live well within that structure, how to maintain coherence and meaning in a world where everything is connected, but nothing is necessarily connected meaningfully. How do you build community in a network where anyone can connect with anyone? How do you maintain identity when you're simultaneously part of dozens of overlapping networks? How do you find truth when information flows so freely and there are no gatekeepers with authority? These aren't technical questions, they're human questions, but they're shaped by the technical reality of the network we've built. The internet's shape creates the conditions for these questions, and we're all trying to figure out the answers collectively in real time. You know, there's a funny thing that happens when you study the internet's shape for a long time. You start to see network patterns everywhere. You look at a city and see nodes and edges. Buildings are nodes, streets are edges. People flow through the network like data packets. You look at a conversation and see information propagating through a social network. You look at an ecosystem and see species connected in a food web, energy flowing through the network. The mathematics of networks, the concepts of topology and connectivity and flow, they apply to so many things. The internet is just one example, one instantiation of these deeper patterns. And maybe that's the most profound thing about asking, does the internet have a shape? The answer reveals something not just about the internet, but about how structure and connection work in general, about how complex systems organize themselves, about the patterns that emerge when many simple parts interact. The internet is, in some sense, teaching us how to see, how to recognize network structures, how to understand systems in terms of nodes and edges and flows, how to think about emergence and self-organization and collective behavior. These are skills that matter beyond just understanding technology. They're ways of thinking that apply to social systems, biological systems, economic systems, political systems. The world is full of networks. The internet just makes network structure more visible, more explicit, more measurable than most other systems. So when you're lying there, drifting off to sleep, contemplating the shape of the internet, you're actually contemplating something much bigger. You're thinking about how things connect, how structure emerges from interaction, how local rules give rise to global patterns. You're thinking like a network scientist, and that's a valuable way to think in an increasingly networked world. But it's also okay to just let it all wash over you, to appreciate the beauty without needing to understand every detail, to feel the wonder of being connected to billions of other humans through this invisible infrastructure, to marvel at what we've built, what we've become. The internet has a shape, yes, many shapes depending on how you look at it. Physical, logical, informational, social, evolving, complex, beautiful, problematic, transformative shapes. And you're inside that shape right now, swimming through it, part of it, connected. So where does the internet end? Where are its boundaries? This is a question that loops us back to the beginning. Because in one sense, the internet has clear boundaries. It ends where the physical infrastructure ends. If you're in a remote area with no cell service and no cables, you're outside the internet's physical reach. But in another sense, the internet is constantly expanding. New infrastructure is always being built. New devices are always coming online. Satellites are extending coverage to previously unreachable places. The boundary is always moving outward, and in a deeper sense, maybe the internet doesn't have boundaries at all, because information can be copied, can be cached, can exist in multiple places at once. That video you're watching isn't really somewhere. It's on a server, but it's also in your device's memory, and it might be in a content delivery network cache nearby, and it might be in other people's devices if they're watching it too. Information is strange that way. It doesn't obey the same rules as physical objects. You can't say it's here and not there. It can be everywhere and nowhere simultaneously. The internet, as a system for storing and transmitting information, inherits this strangeness. Its shape is fuzzy at the edges. Its boundaries are permeable. It's more like a cloud than a building, even though, as we said earlier, the cloud is really just someone else's computer. And maybe that's the most honest answer to our original question. Does the internet have a shape? Yes and no. It depends on what you mean by shape. It depends on what layer you're looking at. It depends on whether you're asking about physical structure or logical structure or informational structure. The internet is like those ambiguous optical illusions where you can see it as a vase or as two faces. The shape you see depends on how you look at it. But all of these shapes, all of these perspectives, they're all real. They're all part of the truth. The internet is simultaneously a physical network of cables, a logical network of routes, a graph of connected information, an emergent system of self-organization, and a constantly evolving social structure. It's all of these things at once, and that's what makes it so endlessly fascinating to explore. You know, there's something deeply human about wanting to understand shape. We're spatial creatures. We navigate the world by building mental maps, by understanding how things are arranged in space. It's one of the fundamental ways we make sense of reality. And here we've built this massive, complex system that doesn't quite fit into our spatial intuitions. It's everywhere and nowhere. It's big and small at the same time. It connects distant places and creates new kinds of distance. Trying to understand the shape of the internet is, in some ways, trying to expand our spatial thinking into a domain where traditional geometry doesn't quite apply. It's like how physicists had to invent new mathematics to understand the shape of space-time, or how we needed new concepts to understand the shape of quantum reality. The internet is the same kind of challenge. It's there, it has structure, but that structure doesn't fit neatly into the categories we're used to, and I think that's okay. I think there's something beautiful about encountering systems that resist easy categorization, that require us to think in new ways, that expand our understanding of what shape even means. Let me tell you a little secret. When computer scientists and network engineers work with the internet, they don't actually worry too much about what shape it is in some absolute sense. They care about specific properties. Is it connected? Can any node reach any other node? Yes, mostly, with some exceptions. Is it resilient? Can it route around failures? Yes, pretty well, though those hub failures are still a concern. Is it efficient? Can data get where it needs to go quickly? Yes, remarkably so. Given how decentralized it is it scalable? Can it keep growing without breaking down? So far, yes, though there are ongoing challenges. These are the practical questions, and they can all be answered without needing to visualize the whole shape in your mind. But we're not computers, we're humans, and we think in stories and pictures and shapes. So even if it's not strictly necessary, there's value in trying to imagine what the internet looks like. It helps us understand it. It helps us talk about it. It helps us recognize patterns and problems. And honestly, it's just deeply satisfying. There's a joy in understanding structure, in seeing how things fit together. So even though the internet's shape is complex and multi-layered and constantly changing, even though it resists easy visualization, we keep trying. We keep making maps and diagrams and models. We keep asking, what does it look like? Because understanding shape is how we understand the world, and the internet is part of our world now, a big part. Maybe the biggest new part of the human world in the last 50 years. Understanding its shape is part of understanding ourselves, understanding how we connect, how we communicate, how we share information, how we build communities across distances that would have been unimaginable to our ancestors. The shape of the internet is, in a real sense, the shape of modern human civilization, because the internet isn't separate from human society. It's woven through it. It's part of the structure of how we live now. And that shape is still being determined by engineers and companies and governments, yes, but also by you, by your choices about how you connect, what you share, who you link to. Every hyperlink you create, every message you send, every network you join, you're adding a tiny thread to this vast web. You're participating in the ongoing creation of the internet's shape. And here's something to think about as you drift towards sleep. The future shape of the internet is not predetermined. It's not inevitable. It's being made right now, through countless decisions, through technological developments, through political choices, through social movements, through market forces, through individual actions. The internet could become more centralized, controlled by a handful of massive companies and governments. Or it could become more distributed, more democratic, more peer-to-peer. It could fragment into separate regional internets, balkanized and isolated. Or it could become more unified, more global, more accessible to everyone everywhere. It could extend into space with satellite constellations and beyond. Or it could become more grounded, more local, more focused on community networks. It could incorporate new technologies like quantum communication and biological computing. Or it could evolve incrementally, building on the same basic architecture we have now. All of these futures are possible. The shape the internet takes will depend on us, on what we build, what we choose, what we fight for, what we accept. And that's both a responsibility and an opportunity. We're not just passive users of the internet. We're participants in its ongoing creation. We're shapers of its shape. All right, we're coming to the end of our journey now. Let's float back up to the surface, back to where we started. Does the internet have a shape? After all we've explored, I think the answer is yes. Many shapes, all at once, all layered on top of each other, all real, all important, all constantly shifting. The physical shape of cables and servers, following the contours of human geography, extending beneath oceans and into orbit. The topological shape of scale-free networks and small world properties, compressed and efficient, with critical hubs and vulnerable choke points. The informational shape of the web graph, bow-tie structured, with a core and a periphery and isolated islands. The emergent shape that arises from billions of independent decisions, self-organizing into patterns nobody designed. The fluid shape of data flow, always adapting, always changing, routing around failures and finding optimal paths. The future shapes we're building right now, with mesh networks and satellite constellations and quantum entanglement and biological computation, and perhaps most importantly the human shape, because the internet is ultimately a tool made by humans, for humans connecting humans. Its shape reflects our needs, our desires, our power structures, our creativity, our conflicts, our hopes, our fears. When you ask what shape the internet has, you're asking what shape humanity has taken in the digital age, and that's a question we're still in the process of answering. But here's what I hope you take with you as you drift off to sleep. The internet isn't just a tool you use, it's a place you inhabit, a space you move through, a structure that surrounds you. And that structure, that shape, it's not fixed, it's not finished, it's not carved in stone, it's alive, it's evolving, and you're part of that evolution. Every time you go online, you're walking through a vast invisible architecture. You're navigating a topology that spans the planet and reaches into space. You're swimming through rivers of data, crossing bridges of bandwidth, exploring the endless rooms and corridors of information. And that architecture, that shape, it's one of the most remarkable things human beings have ever built. A nervous system for the whole species, a collective memory, a space where distance collapses and connection happens at the speed of light. It's strange and beautiful and sometimes troubling and always fascinating. And it's worth understanding, worth appreciating, worth thinking about, not just as a user, but as a citizen of this digital space, as someone who lives in the shape of the internet. So thank you for wandering through this with me tonight. Thank you for exploring these invisible structures, these mathematical patterns, these emergent shapes, these possible futures. I hope your mind is quiet now. I hope you're feeling that pleasant floaty feeling that comes right before sleep. I hope you'll dream gently, perhaps of vast networks of light, of data flowing like rivers, of connections spanning the darkness, of satellites dancing in orbit, of quantum entanglement bridging the void, of a web that encompasses the world, and I hope that tomorrow, or whenever you wake, you'll see the internet a little differently. Not as a mysterious black box, but as a structure with shape and pattern and beauty. A human creation that reflects something deep about how we connect and communicate and build meaning together. Remember, wherever you're listening from, whatever time it is there, you're not alone. You're part of this vast network, a node of consciousness in a web of billions, connected to all of us by light and electricity and radio waves and shared curiosity. You're floating right now in the invisible architecture of the internet. Its shape surrounds you, holds you, connects you to the rest of us. And that shape is still forming, still growing, still changing, and you're part of that change. Thank you for being here. Thank you for listening. Thank you for letting me share this slow journey through the shape of the internet with you. If you enjoyed this, give it a like. Subscribe for more late-night explorations of computer science. Leave a comment telling me where you are in the world. I love seeing our network of sleepy learners spread across the globe. Tell me what time it is where you are. Tell me what shape you think the internet should take in the future. Until then, sleep well, fellow node. The network will still be humming when you wake. Its shape will still be there, vast and strange and beautiful, waiting to be explored. From the sleepy computer scientist, good night. May your dreams be full of light and connection. May you rest well in the knowledge that you're part of something vast and intricate and alive. May you wake refreshed, ready to navigate the invisible architecture all around us, ready to add your own thread to the great web we're weaving together. Sweet dreams, dear listener. The internet's shape will hold you gently until morning. You are connected. You are part of the pattern. You matter. Good night.